We're going to be talking about the atom. No, don't worry, we are not going to get into quantum mechanics yet, but for a couple of videos, I want to introduce you to the atom where you can understand chemistry. Okay? Like I said, there will be a lecture on quantum mechanics, but you can understand chemistry with what we're going to be doing in this video and the next one, the continuation. We already talked about this a little bit way back in the time of ancient Greeks. It was thought that matter consisted of 4 elements: fire, earth, air, and water. This was the scientist. That's what is so amazing. But some philosophers said, no, we really think that the atom is made up of some very small, indestructible, indivisible subunits. That's where the word atom comes from the Greek word for indivisible. Unfortunately, the Dark Ages came, even the Renaissance. The only concern people had with chemistry was really alchemy. How can we convert lead and iron into gold and silver? It wasn't until the 1800s that science took over again. John Dalton proposed his atomic theory, and we are going to see that most of his ideas are correct, and even the ones that he was not right, it was reasonable at the time with what he knew. So his atomic theory can be summarized with 5 points. He said matter is composed of very, very, very small particles that he called atoms, just like the Greeks did, and said the atom is the smallest unit of an element that participates in a chemical change. We agree to that. You'll hear me talking about atoms and molecules. I play with Legos. The pieces of the Legos will be the atoms. So he was right there. An element consists of only one type of atom that has a mass characteristic of the element is the same for all of the atoms of that element. No. We are going to be talking a little bit in this video and a little bit in the next video about isotopes. Those are atoms of the same element that have different masses. Because they were not known at the time when Dalton lived, but that's the only flaw really in his theory. The atoms of one element different properties from the atoms of all other elements. Yes, of course. I mean, oxygen doesn't look like iron, right? A compound consists of atoms of 2 or more elements combined in a small whole number ratio, and it's the same ratio for that particular compound. Once again, atoms are like Legos. You can combine them in ratios, but you don't combine half a piece with 3/4 of a piece. You always have one piece with one piece, or one piece with 2 pieces, something like that. And like I said, that ratio is the same for that compound. If I say water is H2O, means that it has 2 hydrogens for every oxygen. It doesn't matter the source. It doesn't matter if you got it from the chemistry lab, or you got it from the convenience store, or you went to the lake. Water is always going to be H2O. So he was right here. Atoms are neither created nor destroyed during a chemical change. They just rearrange to yield different types of matter. Let me put a question mark in here. This is true most of the time, but when you talk about nuclear chemistry, it could be considered an exception, and obviously there was no nuclear chemistry in Dalton's days, because in nuclear chemistry an atom is transformed into a different kind of atom. They don't just rearrange, they're not really created, but they are at least changed. So that's why I just put a question mark in there. This is an example of what I'm trying to say. You have copper, you have the atoms of copper, you have oxygen. When they combine, you know chemical reaction has taken place because originally copper has copper color. Now it's black, copper oxide. But you can tell that the copper atoms are still there. The oxygen atoms are still there. they just got rearranged. Instead of oxygen combined with oxygen and copper with copper, now you have oxygen and copper combined together. Once again, think on Legos. You can put them together any way you want to, make all sorts of different combinations. Hopefully you don't destroy, you don't lose any pieces, right? So the atomic theory that Dalton proposed gives you a macroscopic explanation for some of the observations that we have seen. Okay? We talk about the law of conservation of matter in the introduction. That's very easy to explain. If all you're doing is rearranging atoms, but you don't create or destroy atoms, of course the mass is not going to change. You look at this example, originally, in the same materials, you have 4 green atoms. In the product, you have 4 green atoms. You have 2 purples, 2 purples. Nothing has changed. That's why the mass is the same. There's another law, definite proportions, that tells you that a compound, pure compound, contains always the same elements in the same proportion, by mass and actually by atom too. So, as an example, Proust studied isooctane. That's the main ingredient in gasoline, by the way. He had a number of samples. He analyzed to see how much carbon, how much hydrogen each one had. You can see that there were samples of different sizes, but when he divided the grams of carbon by the grams of hydrogen, he always came up with the same ratio. It's 5.33 grams of carbon to 1 gram of hydrogen. It didn't matter where the sample came from, the size of the sample, they're always in the same proportion. Like we said before, when you say water, water is always made up of 2 hydrogens and 1 oxygen. Now, some elements can combine in more than 1 ratio. This is a very complicated way to explain it. A fixed mass of one element will react with different masses of the second one, but those different masses are always in a ratio of small whole numbers. To put it in plain English, one atom can combine with 1 atom of another element, or with 2, or with 3, always small whole numbers. And to give you an example, copper and chlorine reacting. They form 2 different compounds because one is green and one is brown. But when you look at the amount of chlorine that reacts with 1 gram of copper, if you look at the ratio of chlorine, it's a 2-to-1 ratio. That's what I say, small whole numbers. Why? Because copper can react with 2 chlorine atoms, or it can react with 1. But it doesn't react with 1.5. It's always whole numbers. Whenever you have atoms that combine in different ratios, keep in mind that they form different compounds with different properties. Let me give you an example. Everybody knows water, right? And water is necessary for life. Hydrogen peroxide, that's what your mother used to use on cuts, scratches, to disinfect. Okay, so let me tell you a joke. 2 chemists walk into a bar, and the first chemist walks up to the bartender and says, "Give me a glass of H2O. Bartender puts a glass, he drinks it, good. The other chemist didn't want to seem like he was less of a chemist than his friend, so he said, "Give me a glass of H2O too." The bartender poured it, he drank it, he dropped dead. Why? Because he meant to say, "Give me also a glass of H2O, but he said H2O too. The bartender gave him a glass of hydrogen peroxide, he died. There's a tremendous difference between H2O and H2O2. So the atomic theory has evolved pretty much since the time of the Greeks, but certainly we're going to be studying Dalton's time. People have wondered, what are the atoms made of? Is there anything smaller, subatomic? And we're going to be looking at some of these developments and how the idea of the atom has been changing. This is a perfect example of a scientific theory, because Someone comes up with a theory, then somebody else does an experiment and says, your theory does not explain my evidence. Okay, so we modify the theory. Somebody else does another experiment. Hey, look at this. Okay, well, we have to modify the theory again. And we're going to see how the theory continue evolving. We're not going to get in these videos to the quantum mechanics, but we're going to go high enough that you will have a picture of an atom that you can use to explain almost anything that we are going to be looking in chemistry. Okay? So it all began with Thomson. Thomson made this little gadget in here. Basically, you had this tube that it was almost at a vacuum, as much to a vacuum as he was able to. He had 2 electrodes. He tried putting different metals for the cathode, and he would turn on a high voltage. Whenever he did that, he could see a visible ray that he called a cathode ray, because it came from the cathode. And what was very interesting is that if he put another electrode halfway in there, they would deflect the ray away from the negative charge. He tried different materials for the cathode, he always got the same results. So what were the conclusions from Thomson's experiments? He said, okay, the particles that make the cathode rays are very light. They're very light because they're flying across the tube. They're not strong enough for the gravity to pull them down. They're negatively charged. We know that because when they get to the negative electrode, they're deflected. Charges of the same sign repel each other. And they were the same regardless of the source of material that he used. They were common to any matter. So he called them electrons, and an electron is a negatively charged subatomic, meaning component of the atom particle, and the mass was more than 1,000 times less than the mass of the atom. Thomson also wanted to know how much was the mass of the electron. He was not able of doing that, but he calculated the ratio of the charge to the mass, and that would be used by somebody else. But at this point, he came up with a model that was called the electron pudding, saying that the atom was made up of electrons just flowing around. That's all there was to it. Okay? That theory is going to have to be modified. But before we change it, another person wanted to find out what was the mass of the electron. Just saying that's very small wasn't enough. So he had this little setup. He was able to create macroscopic oil droplets, and they were electrically charged. Okay? So if you spray droplets of something, what happens? If the droplets are small enough, they're going to come down slowly. Because they were electrically charged, he was able to put an electrical field and slow down the process. Even if he uses enough electricity, he could reverse it. Can you imagine drops that actually fall upwards? By knowing how much electricity he was using, he was able to determine the charge of an oil drop. And please, I don't want you to memorize the number. The important thing, and obviously the charge is going to vary depending on the size of the drop. Not all the drops are the same, but they were always a multiple of a very specific number, 1.6 10 to the minus 19 coulombs. You don't need to know the number, but you need to know it was a multiple of a very specific number. So he decided that that must be the charge of the electron. Okay? That number was the charge of the electron. Then the droplets would have 1 electron, 2 electrons, 3 electrons. That's why the charges were multiples of that number. That was smart, wasn't it? Since Thomson had calculated the ratio of the charge to the mass, now that they knew the charge, he was able to calculate the mass. And again, I don't want you to memorize the number, but 10 to the minus 31 kilograms, that's a very small number. I mean, you're talking about 0.00000, 30 zeros. That was a very, very small number, which was exactly what they expected. It was a very small, very light particle. The next person decided to go further. He's going to aim a beam of alpha particles to a very thin gold foil. Now, he knew the alpha particles were positively charged. He knew what reactive materials he needed to use for that. And he surrounded his foil with a screen, a luminescent screen, so that whenever the alpha particle hit the screen, he could see it. Now, if the electron Putin theory was right, all of the alpha particles would pass through the goal and appear on the opposite side. If gold is solid, like it seemed to be, he expected of the alpha particles to bounce off. So you can imagine his surprise when he saw that the majority of the particles passed through. Some got deflected a little bit, and some actually bounced backward. Now, that's not what was expected. How did he interpret this? He said, well, most of the volume of the atom is going to be empty space. That's what most of the alpha particles can pass through. In the center, you're going to have a very heavy positively charged body that we call the nucleus. And then basically what he was saying, if you had the nucleus here, and let's say this was the whole atom, the alpha particles that didn't get close to the nucleus passed through. And that was the great majority because the nucleus is very, very small. Some came close and got repelled. Why? Because the nucleus is positively charged. That's what he was suggesting. The alpha particles are positively charged, so once again they repel each other. But he said it's going to be heavy because some actually hit the nucleus and bounce off. So the nucleus contains most of the atom's mass. The negatively charged electrons surround the nucleus, and the particles that make up the nucleus, he called them protons because they were positively charged, and they are heavy. So that's a tremendous progress, right? Everything sounds very good until someone discovered isotopes. We mentioned isotopes earlier. We said those are atoms of the same element, but they have different masses. And we're going to see more in the next video. But the only way you could explain the different masses is if there was particles in the nucleus that have about the same mass than the protons, but they were not charged. Okay, so they call these particles neutrons. And now we're saying the nucleus is made up of positively charged protons. There's going to be several of them. Then there's going to be a point zeros for not charged. All that makes the nucleus. And then you're going to have the electrons outside of the nucleus. That's time to get closer to what we know about the atom today, right? The important thing about that is, once again, the nucleus contains the majority of the atom's mass. The protons and the neutrons are much heavier than electrons, but the electrons occupy most of the atom's volume. Don't worry too much about the actual numbers. I like this example because it helps you visualize. If the atom was the size of a football field, the nucleus would be the size of a blueberry. That means most of the atom is empty. Think for a moment, because you hear me say things like that and you say, yeah. It's amazing. You're sitting on a chair, aren't you? And the chair is mostly empty space and it's holding you. And you cannot go through a wall. When we talk about bonding, the bonds that hold the atoms together, that's going to be responsible for the chair holding you, for the wall not allowing you to go through. Still, it blows my mind every time I talk about it. If you know anything about the numbers, and I kept telling you, you don't have to memorize the numbers, but notice how small the numbers. You have there the weight in grams of a carbon atom, 10 to the minus 23, 0.00000. And the charge of the electron, minus 19, 0.0000. Someone said, we need different units, okay? We need small units because atoms and subatomic particles are small. It makes sense, okay? You don't measure the distance cross-country in inches, because the distance is very big. You need to have units that are appropriate for whatever you're measuring, so let's come up with the small units. They invented the atomic mass unit, called AMU, and the fundamental unit of charge. The AMU, you have a conversion there to grams, you can tell it's small. Again, I don't expect you to memorize the number, but the definition is important. So the mass of a carbon-12 atom weighs 12 AMUs. Two things I want to mention. Why carbon-12? Because it's very stable and it's very abundant. So it's a very good reference. And now you can compare the masses of all the other atoms. And if carbon-12 weighs 12, then this atom is going to weigh 1, this atom is going to weigh 15. It gives you a standard. And as far as the unit of charge, again, I would memorize the number. That's the charge of 1 electron. Obviously, 2 electrons would be twice. But in the second semester, when we talk about electrochemistry, this will be important. You can look it up then. You don't need it for college chemistry 1. So we're going to summarize the subatomic particles. The proton has a mass of 1.0073 AMUs. For simplicity, let's just call it 1 AMU. Very, very, very rarely you need the actual number, and you can look it up. Most of the time, we just call it 1 for simplicity. The charge is +1, and we said it's located in the nucleus. The neutron is also located in the nucleus. The mass is a little bit more than the proton, not a whole lot more. You can still call it 1 AMU. And again, for most of what you're going to be doing, that's going to be good enough. The charge is 0. The electron is located around the nucleus. Remember, the nucleus is a very small part of the atom. The mass, look how small, 0.000055. 1 MU is small. What is this? You know what? We are going to call it 0. And once again, for most of the things you're going to be doing, that will be good enough an approximation. And we know the charge is -1. So these, the 3 particles, where you find them, the mass with the approximation that I gave you, and the charge, you need to know. Next, we're going to define atomic number. Atomic number is the number of protons in the nucleus, okay? And it's represented with a letter C. This is a very important number because it determines the identity of the atom. It's easy to understand. You have numbers that identify you. Your social security number, your driver's license number. There's not 2 people with the same social security number, right? Or there shouldn't be. Unless someone stole your identity. Same thing. If you give me a number, 23, out of the blue, I can go to a periodic table and say, 23, that's vanadium. Well, how about 14? Well, 14 is silicon. You can identify the atom by the atomic number. Okay? And again, it's the number of protons. Now, you have to keep in mind atoms are neutral. They have the same number of positive and negative charges, the same number of protons than electrons. So when they give you the atomic number, they're actually giving you the number of electrons. Because if you know the number of protons, it's the same number of electrons. But the number of electrons is not or does not define the atomic number. We always use the number of protons. Why? Because we are going to see that electrons are going to participate in chemical reactions. Atoms can lose electrons, they can gain electrons, they can share electrons. It's like they are very careless. The number of electrons will vary, but the number of protons remains constant. So please, that's a very common mistake. Atomic number is the number of protons by definition. The mass number, represented with A, is the number of protons and number of neutrons. My question would be, why not the number of electrons? Because we just said that the mass of the electrons is roughly 0. So if you want to know how much does an atom weigh, you know the protons weigh 1 mu, the neutrons weigh 1 mu. If you know how many protons and how many neutrons, that gives you the mass number, the weight of your atom in MUs. A very common problem for students is asking them, how do you calculate the number of neutrons? Well, that's very easy. The mass number minus the atomic number, because the mass number is protons plus neutrons. If you subtract protons, then it leaves you the number of neutrons. That is a very common problem, and I don't understand the reason, but seems to be one of the stumbling blocks for many students. Okay. Finally, atoms are going to be represented by chemical symbols. Okay. Some symbols are very easy because they are derived from the common name of the element. So C for carbon, okay, I can understand that. O for oxygen, yeah, I like it. Sometimes you need 2 letters because then you have calcium and you say, well, I cannot use C because I already use it, so I'll call it Ca. Okay, I can handle that. Notice when you have 2 letters, you only capitalize the first one. But sometimes the names come from another language, most commonly from Latin, but that's not the only. Sometimes atoms are named after places. They may be named after people. So I have a few examples in here. Like I said, most of them are very straightforward, but then you see iron Fe. How? Oh, because it comes from ferrum, the Latin word for iron. So you have a few examples of names that come from Latin, but then there's, like I say, some come from places. Looking at the end of the periodic table, berkelium, because it was discovered in Berkeley. You have Einsteinium, named after Einstein. So some of the names are not going to be very straightforward. I would recommend that you start memorizing the most common ones. Okay? You're going to pick up names and symbols slowly. But if you begin by knowing the most common ones, like you need to know nitrogen and oxygen and hydrogen, and we have hydrogen here, fluorine, carbon. I think for the time being, sodium, that's common sulfur. Begin with these ones if you want to include aluminum, because it's easy. And then slowly you will be adding more. For the time being, like I said, just memorize the most common ones so you don't get lost when we start actually doing chemistry. Okay? So once again, if you like to work one-on-one with me, if you want to have access to my worksheets, if you want to study for an exam, find the link to my Wycent account in the video description and make an appointment.